Welcome back. Last time we talked about measuring volatility and mentioned the ARCH model as the most common approach to doing that. In this tutorial, we're going to introduce the notation behind the model, what its parts represent, when we use it, and how to interpret all of this. Right off the bat, we need to make one thing perfectly clear. Unlike the ARIMA family of models, the ARCH ones consist of several equations, including one for the mean and another for the variance. Some of you might be wondering, wait, why do we need several equations? Well, the explanation is rather simple. To measure unexpected shocks, we need some sort of norm, which we set with the first equation. Without such a base model, we don't really have anything to deviate from. Perfect. Now let's discuss the name of the model. As you already might suspect, just like AR, MA, and ARMA, ARCH is also an abbreviation. It stands for Autoregressive Conditional Heteroskedasticity Model. To fully understand how it works and what it measures, we'll break this notion down into several parts. First off, let's look at heteroskedasticity. We need to mention that both spellings are correct, so you can use either one going forward. The word heteroskedasticity comes from ancient Greek. Its literal meaning is something along the lines of different dispersion. As you're aware, the most commonly used measurements of dispersion are variance and standard deviation. And since we have a direct relationship between the two, we are only going to focus on the former. Next up is conditional. In Bayesian inference, a conditional value is one that depends on others. The simplest example of this is conditional probability, where the likelihood of one outcome varies when conditioned to other outcomes. All right. The combination between conditional and heteroskedasticity suggests we will be dealing with variance, which is dependent on other values. But what might these values be? Well, herein comes the autoregressive part. We'll be using past values to measure variance, which is conditional of the variance of past periods. I know it's challenging to imagine all this, so let's take a look at the variance equation for a simple ARCH1 model. Okay, suppose we have a variable y, and we want to apply the simple ARCH model on it. Then the equation will read as follows. The variance of y in period t, dependent on y in period t minus 1, is equal to alpha null plus alpha 1 times epsilon in period t minus 1 squared. Okay, now let's dismantle this model and go over its different parts. We start with the conditional variance, where we see that the current period values are dependent on past ones. In particular, since this is a simple ARCH model, we're only relying on values from a single lag ago. That's why we only have y in period t minus 1 on the right side of the conditional line. Next, we have the term alpha null, which is a constant factor, similar to c from models we've examined so far. After that, we can see alpha 1, which is the coefficient associated with the first term. Moreover, it's equivalent to the theta 1 we used in the ARMA and ARIMA models. The last term is the one we're most interested in. It's the squared value of the residual epsilon for the previous period. Here we see the autoregressive aspect of the model, since we are relying on past values to determine its conditional variance. As you know from statistics, we use sigma squared to express variance. Therefore, we substitute the dependent variable notation with sigma squared t, which of course expresses the variance in period t. Hence, we write sigma squared t equals alpha null plus alpha 1 times epsilon in period t minus 1 squared. This way, we lose the clearly defined conditional aspect of the model. However, we can easily determine its order and do so by counting the number of past residuals we're incorporating, which is 1 in this case. Great! Let's quickly discuss higher order ARCH models before we move on to the more complex topics. For starters, the ARCH contains a single order specification, Q, Just like the autoregressive model, it expresses the number of previous values we include in the model. Hence, an ArchQ model looks like this. Sigma squared t equals alpha null plus alpha 1 times epsilon in period t minus 1 squared plus alpha 2 times epsilon in period t minus 2 squared, and so on, up to alpha q times epsilon in period t minus q squared. Great. Now that we've explained what the model looks like, we're ready to understand what it measures. Thanks for watching. Hi there. We've learned a lot about what these models look like, so it's time to talk about why we use them. We adopt these models when we're interested in volatility, but we haven't clearly explained what volatility is. In this lecture, we're going to do precisely that and comment on several of the main characteristics of them. Before we begin, I'd like to point out there will be no coding in this short lesson, so if you're already well familiar with the concept of volatility, you can move on to the next lecture. Okay, this volatility refers to some numeric measurement of uncertainty, which depends on the volume of changes in valuation. Of course, by valuation here, we most often refer to the prices or returns of said securities, portfolios, or market indices. Due to the nature of the data set, volatility is often not directly observable. That's also true in our case, because we're using daily data. If we had a higher frequency of the data, like recording the data every several minutes, we'd actually have a much better idea of what this volatility is. The main issue comes from the fact that the returns can vary widely throughout the day, and we'd never know if the opening and closing prices are close. For instance, for opening and closing prices that are practically the same, we often observe wide variations throughout a single day. Another important feature of volatility is that it evolves continuously. Since the dataset can't immediately fall into perfect order after periods of turbulence, we rarely have sharp jumps. Next off, volatility doesn't go off to infinity. That's another reason why we prefer the data to be stationary. However, even if it isn't, we can transform it as we've done so far. Another feature of volatility that is pretty much exclusive to returns is how volatility reacts to big increases and big falls. Due to the positive bias toward increases, markets tend to behave differently following fast rises compared to equivalent decreases. To account for this imbalance, economists have developed even more complicated models like EGARCH. If you're curious to find out how this model varies from the regular arch you've just seen, I suggest you look it up online because we feel its niche falls outside the scope of this course. That said, investors prefer stability. Therefore, if two portfolios provide equal returns, but one boasts lower volatility, we choose the latter. Thus, we're going with the choice that has the lowest diversion, so we can have a realistic expectation of the future. The less dispersed the data is, the easier it is to capture most of its variance within a small interval. Fantastic. Now that we know what the model measures, let's explore what we can expect to see in the summarized results. Thanks for watching. Hello again. Last time we mentioned the ARCH models consist of several equations, including the mean equation and the variance equation. We already explained the latter, so now we're going to explore in detail the entire structure of the model. This will help you understand why these kinds of models can sometimes take more time to compute and how to choose the best fitting one. For starters, it's important to note that we can express any variable r, t that we plan on fitting into an ARCH model with the simple equation RT equals mu t plus epsilon t. Just like before, epsilon t expresses the residual values left after estimating the coefficients, and mu is once again the mean. However, here lies the clutch of this model. The mean is a time series, as you can tell by the t-index, so it doesn't have to be 0 or any other fixed constant. It can actually be a function of past values and past errors. In other words, the mean can be modeled using an Armax model. Of course, whether the mean is measured via an Armax model or is a constant value depends entirely on the dataset. Hence, the need to have the mean equation. We often assume the mean is serially uncorrelated. That is, there is no time-dependent pattern. However, at times where one is certainly apparent, we can adopt an ARMA arch model. But how do we do that? We simply use the ARMA aspect to model the variable and leave the arch component to deal with the variance caused by unexpected shocks. Fantastic! It's important to note that we might have a 2-equation or a 3-equation representation of each arch model. The first model is represented by the 3 equations we showed. The general one, where the value simply follows the return and observes some white noise, followed by the mean equation, and of course, the variance equation. Interestingly enough, the mean equation is a function here, which points out that there are no residuals to be included. That's because they're already included in the first equation of the model. Great. That said, the 2-equation representation is the one we're going to use here. In it, we combine the first 2 equations by substituting mu t with whatever function it's equivalent to. That way, the mean equation is actually a model, since it also includes residuals. The common theme in both representations is that the variance equation does not change. Hence, the meat of the arch is consistent throughout. Another important point to explain is how the different equations interact to measure volatility. See, the arch model first fits the mean equation to the data and estimates the residuals. Then, based on the epsilon values we extracted, it measures the conditional variance. Fantastic! Previously, we mentioned that there are no functions which suggest the optimal number of lags we should include for an ARMA or ARIMA method. However, that isn't necessarily the case for arch models. While there isn't a single plot that achieves this, we can examine the PACF of both the variable yt and a squared version of itself, yt squared. Of course, in our case, these would be RT and RT squared, since we want to measure the volatility of returns. We'll refer to this additional time series as squared returns. We've already computed and stored the returns in a column of the data set. Now let's do the same for their squared counterparts. The simplest way to do this would be to apply the mul method and multiply each element of the return series by itself. Okay. To make sure we've successfully created the squared returns, we should display the 2 sets using the plot method. As you can see, the periods of low positive and negative returns are expressed with low volatility, while those with sharp jumps or drops have high uncertainty. Next up, we should look up the PACF of both returns and squared returns. When you pass the datasets as inputs for the method, make sure you start from the second value of the data frame. Just in case you need a hint, we do this because there are no returns for the first period. Generally, the rule dictates that if the time series resembles white noise, while its squared version suggests using an ARN model, we should resort to using an arch-N to model variance. Otherwise, we might have to experiment a bit with different lag values until we find the model which captures the effects best. We've already seen the PACF plot for returns, where the first several lags were significant. Therefore, as much as we want to, we can't directly use the rule of thumb we just introduced. Regardless of that, we should still have a look at the squared values to get an idea about which lags are significant. That way, even though we aren't getting the suggested number of lags, we're still gaining valuable insight on how the data performs. We can see that the first 6 lags are significant, with the first 5 yielding coefficients between 0.15 and 0.25. Such high significant values of partial autocorrelation among the first few lags suggest that there tend to be short-term trends in variance. Another way to think about this is clustering, where we have periods of high variation, followed by periods of high variations, as well as periods of low variation, followed by periods of low variation. This is exactly what the volatility characteristics stated earlier, so our dataset makes perfect sense. Phew! Good job! We've now examined the specifics of the arch model, so we're ready to fit an arch 1 model to our dataset. Thanks for watching. Welcome back. Last time, we went through the notation behind the arch model and explained possible scenarios where it's appropriate to apply it. In this lecture, we're going to learn how to use the arch model method to fit an Arch 1 model. Let's begin. To conduct any of this analysis, we must first import the relevant libraries. Hence, we write from Arch, import Arch model. This is the only new module we need to import for now. Perfect. The next steps we're about to take will feel very similar. First, we'll define a model and fit it to the data set. Once we're ready, we'll display its table of summarized statistics. Now that we have our plan set up, let's get coding. We start off by creating a variable, which will save our model specifications. Of course, we can use the convenient naming system we created early on and call the variable model arch1. We must then set it equal to the outcome of the arch model method. Next, we simply pass the time series we want to measure as the argument variable. In this case, we're talking about returns. Make sure to specify we're only using return values after the first element because its value isn't available. It's extremely important to note that if we don't pass on any values to the other arguments, we'll be using a type of model, which is different from the arch we intended to use. Our goal right now is to learn how to read the summary table. So let's fit this model without giving values to the other arguments, and then print out its summary. Okay, for the time being, we're going to disregard the computational outputs of fitting this model and focus on the summary table. We see the table has 3 parts, so we're going to start with the top one labeled Constant Mean, Garch Model Results. Let's begin with the mean model box, which states constant mean. This implies that the mean is constant, rather than moving, as our previous experience with returns suggested. Below, we see the volatility model, which is labeled as Garch instead of Arch. This confirms that we are using a different type of model for the variance equation. But we'll learn more about this later on. Next up, we can notice normal written next to distributions. This expresses the distribution of the residuals. The method dictates how we find the coefficients, which is the maximum likelihood in this case, as it ought to be. The date and time, of course, express when the fitting happened. Now let's look at the right side of the column. The first 5 are all features we've seen in previous summary tables for regressions, which include the log likelihood, information criteria, and the R-squared values. However, the one aspect we really want to focus on is the DF model, which shows the number of degrees of freedom this particular model has. In other words, it showcases the number of coefficients we're trying to estimate. Since we have 4, we expect to have the numeric approximations of 4 variables shown in the other parts of the table. It's time to move to the mean model part of the table. What we see there is a single variable, mu, and its characteristics. This mu is the same as the one we had in our initial equation, and since we saw this as a constant mean model, we expect only a single constant coefficient to be determined for this equation. Furthermore, the large t value suggests significance of the coefficient, so we know the mean isn't 0. Finally, the last part of the table is called the volatility model, and it's what we're really interested in when we deal with Arch. Let's start from the coefficient names. The omega represents the constant value in the variance. It's what we labeled as alpha null when we introduced the equation. Then we have alpha 1, which is obviously the coefficient for the squared values. Right under it, we have beta 1. Although we're unfamiliar with it at the moment, in less than 30 minutes, we'll know exactly what it represents. Okay, now let's go back and examine the iteration output. Since this model has so many moving parts, it takes several iterations before it converges. This, of course, is due to fitting 2 equations at the same time. But how does it work? It fits a model with certain coefficients, then checks how well it has performed. Afterwards, it adjusts the coefficients before making a secondary check, and so on. Generally, the program stops when the log likelihood decreases. However, in this case, the log likelihood is negative. This means the absolute values have to increase so that the program can stop. Furthermore, since values can be extremely close, there can be some discrepancies depending on the way the functions are coded. Luckily, this feature is automatically programmed in the method itself, so we don't need to worry about when to stop. For more complicated models, this process could take numerous attempts. To avoid needlessly seeing the results for every single iteration, we can set the frequency of the updates. We do this by adjusting the value for the update frequency argument to a higher number, like 5 or 10. Of course, if you prefer to observe all iteration results, you can leave the frequency to 1. Perfect. Now that we know how to interpret the results, let's talk about the correct argument values we need to set to get a simple arch model. Let's start with the mean equation. This model assumes that the mean of the series is not serially correlated. In other words, the mean equation is time invariant, so it includes neither past values nor past residuals. Therefore, we should use either the default constant mean or the more specific 0. Since we don't know whether the mean of the time series is indeed 0, we should just stay with the constant mean approach. Okay, next on the agenda, we have one of the most important alterations we need to make, and that's setting the volatility model equal to arch. We achieve this by setting vol equal to the word arch. However, we also need to specify the order of the model, which is done by giving a value to the p argument. This can be slightly confusing, since we established that the usual order of the arch is defined as q. However, since the AR order coefficient for the ARMA model was called p, we can remember the notation from there. Fortunately, the arch model method is equipped to handle surplus defined arguments. In other words, even if we pass values to the lags or q arguments here, they will be ignored because of the mean and variance models we specified earlier. Good. We have everything set up, so we're ready to fit the model and print out the summary statistics. Thanks for watching. Hello again. It's time to pick up where we left off last time. We set up the code for defining and fitting a simple arch model to the dataset, but we never examined the results. So let's get to it. We see that it took this model only 6 iterations to execute. This means the specifications were loose enough and Python managed to solve the regression in only 6 tries. This implies our model is light and doesn't take too long to compute. Next, we can have a look at the first third of the summary table. Once again, we see the name of the model, and this time it is exactly what we wanted, a constant mean arch model. If we have a look at the right column, we'll see both the adjusted and unadjusted r-squared values. Both are -0, so we need to briefly explain what that means. First of all, there is no such thing as -0. The notation simply means that the value is negative, but its absolute value is so very minute that we should round it down to 0, even up to the 3rd digit after the decimal point. Second of all, we know that the r-squared is a measurement of explanatory variation away from the mean. So, if we're assuming a constant mean, it makes little sense to expect this model to explain that deviation well. In other words, if the residuals are simply a version of the original dataset, where every value is decreased by a constant, then there will be no actual variance. Hence, there is nothing to explain, and that results in a 0 r-squared value. As a takeaway, we must remember that the r-squared is a useful measure, but not for arch models. Moving on, we can see that the log likelihood is roughly -7,660. If you compare this to the values we got for the ARMA and ARIMA, you'll see that the arch value is higher than most. Of course, we know that the log likelihood measures the goodness of fit. Therefore, even the simplest arch model yields a better estimate than the complex multi-lag ARIMA models we referred to earlier. This is fantastic news because it means the higher complexity which we injected by estimating 2 equations simultaneously is immediately paying off by increasing the log likelihood of the model. Okay, now let's have a look at the coefficients. From the degrees of freedom in the first table, we know that there should be 3 of them. Based on how we specified our model, these 3 should be the constant from the mean equation, as well as alpha null and alpha 1 from the variance equation. A quick glance is enough to see this is precisely what we get in the summary table. Now let's have a closer look at the results. We'll start with the mean model section first. When we glance over at the p-value, we usually see some complex scientific representation of the results. More often than not, these numbers include some e minus a number notation. But how do we interpret it? Well, the answer isn't as complicated as it looks. Essentially, to get the actual value, we need to multiply it by 10 to the power of the value after the e letter. Since all the values here are negative, that's the same as dividing by 10 to that power. Thus, very large numbers will have positive values after the e term, while small ones will have a negative one. For example, if we observe the standard error value in the second column, we'll see it reads 1.183 e negative 2. However, we interpret it as 1.183 over 10 squared, which is 100. Thus, the results expressed in regular terms is just 0.01183. Generally speaking, if a p-value has a number lower than negative 2 after the e term, it is significantly different from 0. Going back to the summary table, we notice that the mu coefficient is significant. Therefore, the coefficient value is the baseline we use to determine the residuals for the variance equation. Now let's head toward the volatility model, which we already established is the meat of the arch model. We see that both omega and alpha 1 are significant. Of course, omega here represents the constant term of the variance equation, which we dubbed as alpha null. But why is it dubbed differently then? Well, an extension of the arch model includes another series of variables and its associated coefficients. To avoid confusing the constant as part of the arch coefficients, the Python method we're using adopts a completely unambiguous notation: omega. Great. So we are estimating only 3 coefficients, and all 3 turn out to be significant. Additionally, the log likelihood is higher than that of any of the Aramax family we showed. So, the arch 1 instantly becomes the best estimator of the data we've seen so far. However, it is crucial to remember that the arch can only be used to predict future variance, rather than future returns. Thus, we can use it to determine if we expect to see stability in the market, but not predict if the prices would go up or down. Since the arch method has many arguments, for homework, try setting different specifications to the arch 1 and comment on how they would affect the log likelihood. I suggest you switch up the mean model to 0 or even AR, since we found some time discrepancies in the data when using ARMA models. Just make sure you leave the volatility argument vol equal to arch. If you decide to go for an autoregressive mean model, make sure you specify the lags you intend to use by passing a value to the lags argument. You can input an array like 2, 3, and 6 as the lags if you believe that some of those in between might be insignificant. In addition, practice setting different probability distributions for the error terms. I recommend checking the student's t and generalized error distributions by setting dist equal to t or GED respectively. Now, just as with the ARMA family of models, we should see how increasing the arch order affects estimations. And that's exactly what we'll do in the next lecture. Thanks for watching. Hey there. Last time we saw how the simple arch model measures the volatility of returns. This time, we're going to see the effect of increasing the order of the conditional variance. Let's get our hands dirty with some coding. Since we start where we left off last time, we're simply going to change the value for the argument p from 1 to 2. This is how we define an arch 2 model, so we expect to get similar results. Although we'll stick to the same argument values as before, I highly encourage you to go a step further and see how the simplest of models compare to the AR-Arch ones that you found. For the sake of consistency, we can change the name of the model and results variables to account for this increase in order. Therefore, they would be called Model Arch 2 and Results Arch 2, respectively. You can notice how the number of iterations necessary for the progress to compute increases from 6 to 9. That's because we're estimating an additional coefficient here, the one for the squared residuals 2 periods ago. Next, we can compare the summary tables quickly and see how the log likelihood has increased, while the information criteria have gone down. These both suggest that the Arch 2 outperforms the Arch 1. However, we still haven't checked the coefficients. Judging by their p-values, they're all significant. This is another measurement, which works in favor of the Arch 2, so increasing the order resulted in a better model. We can repeat this same action and compute the values for the Arch 3. If we do so, we'll see that the log likelihood keeps increasing, but by a smaller number. The AIC also keeps decreasing marginally, while the coefficients all remain significant. Since this is mostly a trial and error process, you can try this on your own as an exercise and see for yourself that this pattern persists until the 13th lag, where one of the coefficients, alpha 9, is no longer significant. Of course, including more and more values reduces the additional effects each one has on the log likelihood. In a sense, we are dealing with diminishing marginal log likelihood with each additional lag. In other words, the more past squared residuals we take into account, the less important each additional one becomes. Now, this somewhat resembles the case we had with MA models, where we just included more and more lags until we started getting non-significant coefficients. Well, we amended that case by also including past values as an independent variable. But can we do so here? The answer is yes, and we're going to find out why in the next lesson. Thanks for watching. Hello again. Last time we mentioned improving Arch models by including past values as well. But what exactly would these past values be? Including past returns wouldn't make much sense, since we usually account for those in the mean equation. If we want to draw a parallel with the ARMA, we should include some AR equivalent components. As in the AR models, we'll count on past conditional variances to help us explain current conditional variances. On one hand, this sounds slightly confusing, but on the other, it makes total sense due to the nature of variance clustering. Since periods of high volatility are followed by periods of high volatility, and periods of low volatility are followed by such with low volatility, adding past conditional variances should serve as a great benchmark for estimations. Now, a past conditional variance would already include in itself the effects of previous squared residuals. This would make adding more previous squared residuals redundant. That's why such a model is called the Generalized Autoregressive Conditional Heteroscedasticity Model, or simply GARCH. Next, we'll talk more about its equation, its parallels to the ARMA, as well as how it improves the Arch predictions. Stay tuned.